Welcome to This Explainer. Today, we're uncovering the hidden mechanics, the literal foundation of how massive steel structures stay standing without just, sinking straight into the ground. When you're looking up at a towering skyscraper or walking through a massive industrial warehouse, it's super easy to focus on all that steel reaching up into the sky. But honestly, the real engineering magic is happening completely out of sight, right beneath our feet.
So let's dive right into the core problem here. Steel is incredibly strong. It carries a massive amount of weight. But the earth beneath it? Well, it's soft, and it has a much lower permissible bearing capacity. Basically, it just can't handle that kind of intense pressure. Think about it. If you took a heavily loaded steel column and slammed it directly onto the soil, it wouldn't just sit there. That intense downward pressure would cause it to punch right through the earth like a spear. We have to somehow broker a physical negotiation between ultra-dense, highly stressed steel and relatively weak, yielding dirt.
Here's our roadmap for how we're going to do this. First, we'll look at the load transfer problem itself. Then we'll check out fasteners, your bolts and welds. After that, we'll move through simple slab bases, gusseted and moment bases, deep pocket bases, and finally, we'll look at spreading it all out with massive grillage foundations. Okay, part one, the load transfer problem, steel versus soil. We're starting with the why of our journey, looking at the immense physical stakes when these two totally opposing materials meet. It really all comes down to safe bearing capacity. Soil simply cannot handle the concentration of force that steel can. Every single ounce of weight, every gust of wind hitting the building, even every piece of furniture inside, all of it ultimately has to be transferred to the ground safely. To put that into perspective, a single structural column might carry an extreme axial load of, say, 3,500 kilonewtons. That acts exactly like a needle pressing into the weak dirt. I mean, that is a phenomenal amount of force concentrated onto a very, very small cross-sectional area. Without some kind of clever intervention, that 3,500 kilonewtons would effortlessly slice downward, causing catastrophic settlement. Literally, the building would fail. Enter the column base. You can think of it like a massive adapter cord, or actually, a better analogy, it's like a snowshoe. It's negotiating the immense pressure of that steel down into a much wider, manageable footprint for the concrete and the soil. Just like a snowshoe spreads your body weight over a wide patch of fluffy snow so you don't sink up to your knees, a column base expands the footprint of the steel. Because of this, the soil beneath barely even registers that there's a towering structure sitting right on top of it. Moving on to part two, fasteners, specifically bolts and welds. Before we get into those massive bases I just mentioned, we need to look at the crucial micro-components. These guys act as the structural glue along the entire load path. Look, you can have the absolute best foundation in the world, but if the connection between the vertical column and the horizontal base fails, the whole system collapses, no question. This is where precision engineering really takes center stage. So, understanding the specific shear strengths of these tiny bolts is absolutely essential. They are the first gatekeepers for all that transferring weight. For example, a single 16mm grade 4.6 bolt gives you a precise single shear strength of exactly 29 kilonewtons. Engineers have to calculate exactly how many of these bolts are needed to handle the load so they don't literally shear apart. And they have to follow strict geometric rules too, like the maximum pitch distance between bolts, just to make sure the metal plates themselves don't buckle under the crazy strain.
Now, engineers have to carefully choose the right micro-fastener to handle this initial energy transfer. Bolts are great because they offer predictable clamping forces, especially when you tension them up to their proof stress. Welds, on the other hand, give you this incredibly rigid, seamless connection. But welds come with their own strict set of rules. Like, did you know the effective length of a fillet weld is actually its total length minus twice the weld size? Yeah, every fraction of a millimeter counts when the forces are this intense.
All right, part three, simple slab bases. Let's see how these microfasteners build into our absolute simplest foundation solution for standard axial loads. When your loads are relatively moderate and pushing purely straight down, purely vertical, a simple, elegant transition is really all you need to safely hand that load off to the earth. Here is the exact step-by-step physical path the load takes. It's like a highly controlled waterfall of kinetic energy. The force travels down the steel column, hits the welds, spreads horizontally across a thick, flat steel base plate, transfers right down into a concrete pedestal as a uniform pressure, and finally, it's safely absorbed by the subsoil. That flat steel base plate is providing a rigid, completely uniform pressure distribution right into the concrete. It's the perfect first stage no-show. Now, you'll also notice grout is carefully added beneath the plate. And that's not just some cheap filler.
It ensures 100% solid contact and allows for tiny millimeter-perfect vertical alignments during construction. Meanwhile, you've got these embedded anchor bolts, ensuring the column stays perfectly positioned. They lock the whole shebang right in place. Let's step it up. Part 4, gusseted and moment bases. As loads get heavier or a bit more unpredictable, a simple slab just isn't going to cut it anymore. We have to upgrade the complexity of our adapter. Think about it. If we just kept making a simple slab base bigger and thicker to handle massive loads, the required thickness of that steel plate would become impossible to manufacture and honestly completely impractical to even try to lift. So, when the force gets incredibly high, we shift to a gusseted base. This is where we add these wing-like steel plates to help spread the burden laterally, without needing a comically thick base plate. By riveting or welding these vertical gusset plates and angle cleats under the sides of the column, the stress gets distributed over a much wider area before it ever even hits the horizontal base plate. It's an incredibly efficient use of geometry to save on sheer material weight.
Now, what if the column wants to bend or tip over? The pressure on the base isn't just flat down anymore. It creates tension on one side, quite literally trying to rip the base right out of the ground. We call this a bending moment, and it's exactly what happens during heavy winds or earthquakes. Suddenly, the load isn't just pushing down. One side of the base is digging fiercely into the concrete, while the other side is desperately trying to pull away and lift up into the air.
As that bending moment gets more severe, the load eccentricity shifts the pressure, and we have to rely entirely on heavy-duty anchor bolts to prevent total failure. It works like this. If the eccentricity is small, the whole plate stays in compression, pushing down. But once that tipping force crosses a specific mathematical threshold, which is greater than 1/6 of the plate length, tension begins. At that point, those anchor bolts, they aren't just there for alignment anymore. They are actively fighting immense pulling forces just to keep the building upright. Okay, part 5, deep pocket bases. But what happens if the soil at the surface is completely unusable? Like forcing us to abandon our whole snowshoe horizontal spread idea entirely. Sometimes you simply can't spread outwards because the surface dirt is practically mush. In these cases, engineers actually have to completely flip their strategy upside down. Instead of spreading out, pocket bases plunge the steel directly down into deep piles or well foundations. We just stop trying to gently place the load on top of the ground. Instead, we drive the column deep into a prepared vertical pocket, relying entirely on the friction of the deep earth, tightly gripping the sides of the foundation to hold everything up. It's a totally different approach, using embedded shear connectors and vertical friction to lock the column safely into the earth. The steel column gets fitted with an end plate and multiple horizontal shear connectors. These are spaced out really precisely, usually like 5 times their diameter. Then, the whole assembly is dropped straight into a trench and encased entirely in concrete. The load transfers outwards radially through two-way shear stress, basically gripping the earth from the inside out. Pretty cool, right? Finally, we reach part 6, the grand finale, spreading out with grillage foundations. What do we do when the loads are extreme and the soil is incredibly weak? This right here is the ultimate challenge in structural engineering. It requires the most massive, intricate foundation solution we have. When a simple plate or a gusset just isn't going to cut it, engineers deploy a grillage foundation. This is a massive, multi-tiered grid of steel beams. Instead of a single flat plate, I want you to imagine a woven lattice of solid steel beams stacked crossways right on top of each other. This structure creates an absolutely enormous, rigid footprint of unyielding mass. It effectively acts as an artificial rock just floating on top of soft soil. Now, to make sure these huge steel tiers act as one unbreakable unit, engineers have to follow incredibly precise rules. For instance, the beams remain unpainted, and you have to leave exactly a 75mm clear space between the adjacent flanges. That specific gap ensures the M15 concrete flows in perfectly around everything, locking it all into a single, unified block. And it needs to. This setup solves extreme situations, like supporting a massive 2,750 kilonewtons of combined load over really weak soil. You can think of the top tier as the first wide catcher's mitt for the load. It usually has fewer beams, maybe around 3, and it takes the punishing, concentrated blow right from the column base above. Then, it passes that weight down to a massive bottom tier, which might have 10 or more beams running right angles to the top ones. That bottom tier finally gently hands the weight over to the earth beneath.
It really is a stunningly effective cascade of stress distribution.
So, as we wrap up this explainer, I really hope you walk away with a profound appreciation for this invisible, highly structured journey that keeps our modern world standing tall. Next time you step into a sprawling industrial hall or a towering high-rise, just take a second to remember that right beneath your feet lies a hidden, beautifully engineered world of bolts, welds, gussets, and massive steel tiers, continuously holding back the crushing weight of gravity. Thanks for joining me to uncover this hidden engineering marvel.